Hello, today I will be talking about cellular automata, specifically neural cellular automata. I will be discussing what it is and how it is different from regular cellular automata and its applications in machine learning. So, cellular automata is a set of mathematical rules that govern the state of a system, usually based on the previous state of the system. They can show how simple rules can cause complex structures and patterns to emerge. This characteristic is used often in various simulations of different scopes, emulating different aspects of our world. For a simple cellular automaton, we take a grid of cells representing the system. Each cell can have a state of 0 or 1. We then set the next state of all the cells based on the predetermined rules. Usually the previous state of the system, specifically the neighboring cells, are considered for this. This process is done iteratively for as long as we decide or until a termination condition is triggered or the set number of iterations have been completed. In the case of neural cellular automata, the grid cells can have a value anywhere in between 0 and 1. This makes the grid continuous. On top of that, we use an activation function to increase the complexity of the simulation. An activation function, if you are not familiar with deep learning, is a function that introduces non-linearity inside a neural network. After having a dot product of two matrices, we apply the activation function. This combination gives rise to very complex and interesting behaviors. Neural cellular automata can also be called recurrent convolutional neural networks if we update the filter to reach a desired behavior. They have been used by machine learning scientists to create self-healing structures. If we start from a deformed state, it would iteratively shift the state towards the target state it was trained on. Due to their characteristics, they have been used in biological and ecological simulations, predicting the state of an ecosystem if a certain environmental change happens. They have also been used for physics simulations, namely fluid and fire simulations. Their rule-driven approach can be used to create fast and simple alternatives of otherwise computationally complex and large simulations. Many of the physics simulations are notorious for their complexity and large computational requirements. To implement a basic neural cellular automaton, we would need the following modules installed and imported, namely NumPy for efficient numerical computation, SciPy for the convolution operation, and Matplotlib for visualizing our simulation. We now initialize our grid as a two-dimensional array of random numbers between 0 and 1, and we set its type to float 32 because we need floating point precision to make it continuous. Setting its type to integers would make it discontinuous, undermining the entire point of neural cellular automata. Then we also initialize the kernel, which would be our rule set in the case of neural cellular automata. We initialize it also as a two-dimensional array of random numbers between 0 and 1 with 3 rows and 3 columns. Then we normalize the kernel so we can have negative and positive weights, creating darker and brighter areas in our system respectively. Then we create a plot with Matplotlib, which would be used to display our cellular automaton. We would update this plot once every frame or every step of the simulation to show the progress of our simulation. Now we move on the update function of our simulation. This function will be responsible for performing each step in our system. We perform the convolution operation. This is the operation where the new state is created from our previous state by taking the dot product of the kernel with a group of neighboring cells in our grid. It is important to note that we are wrapping the boundaries. Without wrapping around, the boundary pixel would always be 0. This might cause darker regions in our simulation or might cause things to die as they reach the edges. Then we dampen the changes we intend to do to our grid by reducing our changes by half. We do this to make our simulation run slower and smoother to visualize. Now we apply our activation function. For this example, I am using a rectified linear activation function, otherwise also known as a ReLU function. Then finally, we min-max normalize our grid. That is to make sure that the values stay between 0 and 1 to avoid any exploding effects. With our update function ready, we can start the simulation. I want to run it at 60 frames per second, so I am using a frame interval of 16 milliseconds. You can adjust it accordingly. Here are some of the noteworthy results produced by the program.